Traverse the weights, not the pixels. That is the whole idea. A team from Hefei University of Technology and Kochi University of Technology rebuild large kernel depthwise convolution as a windowed batch matrix multiply, and the operator flips from memory bound to compute bound. The payoff? A 7.8 times larger per layer receptive field at the same speed, and up to 3.72 times the throughput at large batch. The bottleneck. Depthwise convolution is memory bound. Each output gathers k-squared scattered neighbors from non-contiguous rows, blowing the L1 and L2 caches for only one flop per loaded element. Making the kernel larger to grow the receptive field just makes the gather worse. And the existing fix, the large kernel acceleration kernels shipped in RepLKNet and UniRepLKNet, are tuned for small feature maps. On a 224 by 224 map at batch 128, those kernels are 80% slower at 7 by 7 and 89% slower at 13 by 13 than the unaccelerated baseline. Wbmm inverts the paradigm. Instead of gathering scattered inputs, it traverses the parameter table. Partition the feature map into contiguous, non-overlapping W by W windows. Build a per-channel weight matrix M from a compact relative position bias table R. Apply it via batched matrix multiplication on those contiguous blocks. M is batch independent, built once, cacheable at inference. Arithmetic intensity rises with window size, so throughput improves with larger windows and larger feature maps, the opposite of depthwise conv and the opposite of the LKA kernels. The operator level numbers, single A800, 256 channels. Wbmm with 14 by 14 windows against the 5 by 5 depthwise baseline at the 14 by 14 map size, batch 4, 0.45 times slower. Batch 16, 0.62. Batch 64, 1.86. Batch 128, 3.17. Batch 256, 3.72 times. Throughput climbs with batch because the operator is now compute bound, not memory bound. 7.8 times the receptive field, 196 positions versus 25, and faster once batch is at least 16 and the map at least 28. Where Wbmm pulls away is at large feature maps, exactly where the LKA kernels break. Throughput in kiloframes per second against the 13 by 13 LKA operator at 14 by 14 maps, Wbmm 1276, LKA 450, at 56, 63 versus 12. At 112, 15.1 versus 1.7. At 224, 3.83 versus 0.22, a 17 times gap. The LKA advantage collapses as the map grows. The Wbmm advantage widens. Here is the physical picture. A standard large kernel depthwise conv reaches across the feature map by pulling scattered, cache-busting gathers from distant rows, a cloud of disconnected dots. Wbmm instead tiles the map into contiguous windows and applies one structured matrix, multiply per window, an ordered grid where the neighbors it needs are already local. On ImageNet 1000, Wbmm-T matches UniRepLKNet T at 83.2% top 1, but trains in 6 minutes 18 seconds versus 9 minutes 3 with LKA, a 1.44 times speedup at 9. The gather becomes a block multiply, and the cache stops thrashing. At the model level, accuracy is a tie, speed is the win, to 12% less memory. Segmentation and detection gains are real but small, ADE 2020K plus 0.2 MIOU, COCO plus 0.1 AP. The contribution is parity accuracy at higher throughput, not a new accuracy frontier. First, the headline speedup spans two baselines, 1.31 to 1.5 times versus the LKA accelerated UniRepLKNet that ships in practice, up to 1.88 times only versus the slower. 3 honest caveats, non-accelerated baseline. Second, the 3.72 times operator peak is single layer, not the end-to-end model where the speedup is 2 to 3 times smaller. Third, the weight matrix M scales as W to the 4th, memory prohibitive beyond 28, so the speedup is scoped to the tested 7 and 14. Wbmm rewrites large kernel depthwise convolution as a windowed batch matmul over contiguous blocks, flipping the operator from memory bound to compute bound, delivering a 7.8 times larger receptive field. Cite the paradigm flip and the operator level widening gap, not a blanket model win. Traverse the weights, not the pixels. And a widening throughput lead at large feature maps, while honestly flagging that the headline speedup is operator level and baseline selective. Subscribe for the next breakdown.